Alright, so let's construct our sphere here. We are in millimeters, good. And we're gonna work on the front plane. And let's do a line. It's gonna be a midpoint line. And it's a vertical line. And just be sure, yep, no problem. Now let's do an arc, a 3-point arc. And that's gonna be here, here, and that will do. Now let's pick the dimension of that line would be 50, and still on this on the blue, so let's check on this one. That's gonna be 25. We accept that as well. So now everything is dark, fully defined. So now let's go to feature and let's do revolve, this one here, and let's pick the axle. It's gonna be this guy, and 360. Everything looks good. We accept that, and it's done. There we go. Beautiful. So we got our sphere now. Kind of looks good, right, with this rendering, the way they look. I can give the material. Actually, let me specify the material just in case you want to compare where the design is right or wrong. Let's give an IC304. So we apply, and now we got IC304. We are out of here. Change the color, very smooth now. Now let's go back here to evaluate, and evaluate, check the mass, and the mass is showing someplace else. Let me move it here. Is the mass for that sphere is 523.60 grams, more than a pound, on a 50 millimeter 2 inches side ball. Well, that will do. So now let's go and do some flow simulation on this. So if you don't have this tab open, you definitely can go here and do add in, and add in, check whether you have it or not. Like for example, let's see, where is it? Here I have it here, Solidworks flow simulation. There we go. Solidworks flow simulation is right here. See, it's already picked, so I don't have to worry about it. But if you don't, then you will not be able to see this. So now I see it. So let's hit it, and now I have this. Go to the wizard, and we need to save the document. We say OK, and we're gonna save it. And let's create a folder for this, and let's call this sphere. And let's save it there, and it's gonna be sphere. Save. Let's call it Rep1, just to like to call things the way I'm doing it or creating them. So it's gonna be Rep1, and now let's go to wizard, and let's give a name. This is gonna be validation of coefficient of drag or sphere, and next we're gonna use SI unit, no problem there. Anything else here that I would like to change, you can change it here if you want to, but it looks good so far. So next, now internal, it's gonna be external, so the computational domain will be based on whatever Solidworks put together. Now gravity, let's say gravity yes, and so this is 0. Now gravity is minus here, it's going to be on the y direction, so it's minus 9.81, and we are looking good. Anything else? Next. Now it's going to be see, real gases here, real gases, or actually gases, whatever is predefined is air, so add that. Now laminar and turbulent, well, that's a very important question, and so let's go back here to my Excel table and let's get something going on here. Let me delete some of these things that are not supposed to be there, but it's more like to have an idea. Now let's work on 0.003. I have this graph that clearly tells me the drag coefficient for a sphere at a given Reynolds number. So the Reynolds number, depending on the d, in this case is 0.05, that's the diameter in meters, the density 1.2, the kinematic viscosity 1.552 times 10 to e to the minus 5 meters squared per second, and that the area based on this is that number. So everything looks good, and you can see that the Reynolds number here goes from 4 to 4.5, 10 to the 5, so that I can stay here somewhere. Don't exceed this curve that was created for a sphere. So now, with that said, like for example, what will be in this case the coefficient of drag, in this case for when Reynolds is 10. When Reynolds is 10, it's actually right here. That's 4, no question asked. So that's what we're gonna hit. So Solidworks need to calculate the force on the sphere, and from that force we can calculate the coefficient of drag. So like for example, if I put a number here, this already has a formula, so we can take a look at that formula. Basically is whatever is the force that you calculate on Solidworks divided by 1/2 of 0.5 times B$4, that's the density in kilograms meters cubed, and times B6, that's the area of a disk, times the velocity square, and that's 892 square here. So that everything looks good there. So I only need the force calculation, and that will substitute here. But I will also create this coefficient of drag within Solidworks. That will help me to expedite this. So again, the idea is when I hit that wind speed of 0.003 meters per second, pretty much nothing, and I'm definitely deep within the laminar flow, I can go into Solidworks and say, hey, instead of being laminar and turbulent, let's use laminar for it, because I know, and that will expedite some of the calculation faster. So we hit next. Now roughness is a smooth sphere, as you remember, that's right there, and nothing to change there. Now here's the story. We are moving in the x direction, so I'm gonna put the wind speed is in this case 0.003, and the velocity is and divided by a 3D vector. Good, and it's right there. That's the vector. You can see it there. It's a blue color, and that looks good. So I guess we are done here. Nothing else to do. Finish. And now Solidworks prepare for us that huge box. In the meantime, I'm gonna leave it the way it is, but definitely I want to kind of reduce it time, when I do more testing on this. But so far, let's say, and here's the story. So the computational domain was defined by Solidworks. I'm not doing anything, but you can change it at a later time when you have a good idea of how the result looks like. For example, one thing that is very important here is the mesh size. So for the mesh, the global mesh right now is on 3. Maybe I can increase it to 4 and leave it there. So let's say okay, and now let's do let's run that mesh so that you can take a look at it, and let's see how that looks like. So we're gonna run only the mesh. Create mesh, and right now it's running the mesh, and let's see how many cells we end up having. About 86,000 total number of cells, and 288 are having a contact between the fluid and the solid. That looks good. Now let's close this, and now let's look at the mesh here. Insert, and it's gonna be, let's see, let's see, actually it's gonna be YC. Let's see, no, YX, that plane there, right? That will do. Let me take a look at it, and that's it. See, that's how the mesh looks like for this calculation, and no improvement around the boundary around the sphere. So we'll see how good result we get or bad based on that mesh. So we got the mesh. Now let's go. What's going to be the goal? We definitely need at least one goal, which is let's insert a global goal, and that would be what is the total force on the sphere on the direction of X. So that force is right here, force in X. All right, X. We have other forces like Y and Z. We can add it as well for conversion, but the important one is force in X. That's the one that you really want, because that's the one that you will use for calculation of the coefficient of drag. Now with that done, so we accept that, and we have it right here, the goals. Now we need another goal, which is insert equation goal, because that's the coefficient of drag. That's going to be a calculation, a full calculation. For that, what we need is this force. It's going to show there. We need that force, and that force, that's the force in the X direction. That's going to be divided by 0.5. You remember that equation? Let's go back to here to Excel. What I'm doing is actually like let me get this out the way here. What I'm doing is what is here in this equation. Let's see, 0.5 times B$4. B$4 is the density, and we're gonna go back the density, but we need also the area. That's B$6. So now that I'm here, I'm gonna copy this. Let's copy that one. Oops. Let me hit undo here before I'm screwing something here. There we go. There we go. Now let's copy this, and that number need to go back here. So in the order of thing, that's time 1.2 was the density, time the area. What's the area? Control paste, so you see the area there, and that time the velocity. But the velocity, that's a parameter. You can look at right here anywhere. Let's see, input data. From input data, you need general settings, initial this condition here, and that will be velocity in the X direction. So we hit that, and that velocity, it gave you the value, which is 0.003 right here, and that value need to be square. So that need to be elevated to square here, and now close the parentheses, and between this parenthesis and this one is what is on the denominator. All that is the denominator, and that's the force. So eventually this will be the coefficient of drag. And I think we are done here. Anything else that we need to do? Oh, that looks good. So we accept that. And now we have the coefficient of drag, which is an equation, but these are the forces that are going to be calculated by Solidworks. Now, what else I need to do? I need to, before doing anything else, let's go to the solve calculation control option. And now I have all these forces here, but coefficient of drag, I want to do this on manual. And I leave at unit. Let me go back and check on that one, cancel, because it has unit and it shouldn't have unit at the definition. And I left the unit of force here. Coefficient of drag does not have unit, no unit. Good. So we accept it again. Not that it will change the number, but then it will be kind of a weird. So now we are ready down. Now we have the coefficient of drag the way it should be. So we go back again to calculation control. Coefficient of drag, you see no unit. Now we said it's gonna be manual. And I know that I can use also here absolute value has to be less than a value. You know a value, then that coefficient of drag need to hit there at that wind speed of 0.003. So let's do manual still. Let's do manual, and the value I'm going to do a percentage of change. Let's see, 3% is too much. Let's reduce that to 0.05, and let's see, there we go, 0.05 percentage, and we accept that. I think that we got that. Now one satisfy, here we put all satisfy, and look good. That's okay. So we got that. We got already the mesh, and let's run this. Anything else that I need? No boundary condition at this point, no fluid subdomains, only one fluid. The computational domain is as per Solidworks, and the mesh put on 4, and you can see it right there. I don't have anything else except to run this. New calculation, run. Now we go back here, and now we go back here, and we put all of them so we can see them. What's happening? Coefficient of drag is dropping, and the average right now is 12, but it should drop. I know if we go back to my graph, to my Excel, with a 10, Reynolds 10 should be 4, around 4. 10, that's this line here. That's straight, that's right, 4. Now we go back here, and right now it's 4.49, and but that's the current value, but the average is still high, so this needs to go a little bit more. So we wait here. So let me stop recording and I'll be back. All right. Within 10 minutes got solved, and the results are here. 4.35742, that's the coefficient of drag based on Solidworks, and the result as per the graph is about 4 shown here for that wind speed of 0.003 with a Reynolds number of 10 in the laminar region. And let's take a look at some of the things that Solidworks can provide to us, like for example, so now let's do a cut plot, insert, and on that plane, that look good, front plane, see? And 0 meter meaning is right at the middle of the sphere, and contour, so let's say yes, and there we go. And you can see that all this that is in red is a waste of cells on the analysis, so I can definitely reduce a little bit the computational domain. but you can see the different winds, the different wind speed as the air approach the sphere, and what is coming on the back of it, pretty much nothing, like zero. All right, now what else I can do? I can certainly do flow trajectories. Let's see, insert, and that will be, let's put like I don't know, 50 lines, and all right. Now let's hide, because the two together it's kind of hard to see what's going on. Let's hide these so you can see what the wind is doing in terms of I need more lines because I hardly see anything on the back of it. It's a laminar flow, not much to see. All right, so anything else? I look good. So what let's do now the goals here. Let's close these. Actually, let me hide everything here. Flow trajectory, let me hide that. And on goal here, last one, let's insert goals. Let's pick what I really want is on X, this global, really what I'm interested. And let's say show, and it's right there. I got the force actually and the CD definitely. Let's see, there we go. Coefficient of drag 4.35, and the average value, where are the average value? Right here. So I got 4.35, 4.36, and I can copy this, and well, I can copy the whole table, but now that I have this, I can copy that at 0.003, and here's the force. Paste that value. And you get the 4.36, which is what was calculated as well using equation by Solidworks. So looks good. Now that was on the low side. Let's do got it, testing. All right, so got a power shut down somehow, and I'm recovered for it. And so let me see if I can keep recording. Now I'm gonna do the point here for a wind speed of 10. That's a Reynolds number around 32,000. 32,000. This is 10,000, 20,000, 40,000, 32,000, somewhere here. It's very close to this line, and that line is 0.4. 0.4. That's what you see here. Coefficient of drag 0.4. Now, so we're gonna change the wind speed, but now we are in the turbulent region. Definitely. So we go back here to Solidworks, and so let me get out of here, close this, and close this as well. I'm not doing anything else. Now here, let's go to computational, actually to input data. Yeah, I can, what I will do, let me see if something. What I will do at this point, let me close everything here. You see, I got this, but this was done at if I go back here, when the Reynolds number was 10. So basically, I can change the name of this, and let's see if I can change the name. Instead of the variation coefficient drag for a sphere with a Reynolds number, let's see. The Reynolds number was about 10. Now I'm gonna copy the whole thing. Let's see. We're gonna clone that clone, and now we're gonna change the name. Instead of be Reynolds the 10, we're gonna do Reynolds of 32,000. 32,000. We go back here to Excel. 32,216. 32,216, and we save that, and now we are right there. You see, Reynolds number. And what we're gonna do, we got everything the way it's supposed to be here, but except that we need to change the input data, general settings, and we go to initial ambient condition. Well, a couple things need to be changed. Actually, here instead of 0.003 in the x direction, that's 10 meters per second. And let's keep analysis type. Gravity is on, that's okay. Fluid, laminar. We're gonna change here turbulent only, and this one we're gonna do both on the next one, turbulent and laminar, just to see. And anything else look good, apply, and that's 10 in the x direction, and let's see if you can see it. Yeah, right here. See, that's the vector. This is the vector for the direction of the wind and the x direction. Good. Anything else here? No, looks good. Apply. We are out of here. Okay. So now we change the wind speed. Now everything looks good. There's no result to see. Let's see the global mesh where it is. It definitely must be in 4. Yep, that's 4. So we're gonna keep it there. And let's run. I like to run the first thing. Get here in mesh and create mesh. We say run, and so that result will be loaded here just for your inspection, as always, like we did last time. Mesh only, because that's the only thing we have done. And so we can take a look here, mesh show, and no changes from the analysis that we did before at Reynolds 10. Now with that, let's run this. Let's see what happened. And we are pretty much done. Run. Let's check again on the solve here, just to be sure that we're okay. 0.05 coefficient of drag, all satisfied, good. Travel, goal conversion. Everything look good, so run. New calculation, and here we are. And we go back here to this one here, coefficient of drag, and we know that need to be hit 0.4, and it's getting right there very quickly. Right now it's a little bit below, although the average is higher, so we'll see when this stabilizes.
A few minutes later.
It's not gonna get any better. So let's stop. It's not gonna get better. So let's see something here on the input data, general settings. We're gonna be running, as you remember, this system. Let's see. Here, 10 meters per second. That's we're gonna be on the turbulent region. That's about 32,000 or so. And then turbulent parameters. This was left here at those parameters. These are the default from Solidworks when we were in the laminar region. I'm gonna change these to energy and dissipation, and these are the default value. Seems to me, based on experience, that for a turbulent region, truly, when you have all that vortices, etc., this is a better approach than this one. So we're gonna use that one. We're gonna apply that. We say OK. Now everything else is set. Let's run the mesh again. Create mesh. That mesh is as before. That's 4. You remember. We can go here. Oops, still running. You can see it here. Let's see what we got here. Insert information about 86,288. Good. Now let's see. Anything else? Since this is a copy of the first one, everything should be okay. So calculation control, manual, 0.05, all satisfied, all criteria. So we say OK, and basically we run. New calculation, run. Now going back, let's leave this run for a little while. There we go. Coefficient of drag, everything else. 18, dropping, should be around 0.4 or so, or less, 0.48, 0.4, 0.39, 36, 38. Let's see. That looking good. 0.4. That's 0.4 basically, more or less. Let's see. If I go here, back again at 32,000. This is 10,000, 20,000, 40,000. 32,000 should be somewhere here, which is about 0.4, a little bit above 0.4. Will be hard, but definitely slightly above. Might look another velocity that will provide some Reynolds number somewhere here, but my expectation is that be somewhere here around 0.4. That's this is 10. So we are trying to validate that point as well. So let's go back here and let's see where we are. 39.39. Let's allow this to run, and I'll be back.
A few minutes later.
All right, so I left this for run for about 5 minutes, and the number are not changing much. This is pretty much done. So I'm gonna stop it. I'm gonna call for 0.39 basically on the coefficient of drag, 0.39, and so I'll stop here and let's save it. Let's say yes, and let's copy this for so that I'm gonna validate this 32,216, and let's see what happened. Let's go back to, in this case, to my Solidworks, and let's see what we got here. Let's take a look at the cut plot. Show. Yeah, not much. All right. Cut plot again. Play. There we go. All right, and that looks good. I don't see a big deal here. Let's show the result. Where are they? The result. Go plots, insert, Let's take all them, let's show them, and here is the, where's the force? Here's the value, the average value. Copy. We take that to Excel, put it here at 32,000, paste, and that's it. About 0.39, the coefficient of drag versus 0.4, although 32,000 somewhere here, I would say slightly above the 0.4, but hard to tell on this graph, but that's what it is. Anyway, that's not bad. 0.39. Let's see something here again. All right. So all right. Now, what we should validate, another point to validate will be somewhere here, maybe this deep when it goes here, and that's 4.5. That's 140 meters per second. So let's try that as last try on this. So let's get out of here, and let's validate that last one, and that will be going here, input data, and general settings. We go here, and definitely we're gonna put 140 here. 140 meters per second. Leave everything the way it is. Turbulence parameter, very important to be left at there, at that parameter. Turbulent energy and dissipation. We apply. We say okay. Everything is as the way it was. So let's run this new calculation, and let's see what's gonna happen. We're here now. And the expectation is that that coefficient of drag here is 0.08, 0.08. So that's this one here. It's touching somewhere here. It could be a little bit higher, but you know, between 0.08 and 0.1, that would be good enough for the calculation. We'll see. So go back here and let's see what's going on. Still very high, and that's not good. It's dropping, but it's not dropping fast enough, and I don't think that that will converge. Might need to adjust something else, or more parameters need to be adjusted. Stay around 0.2 and 0.24 somewhere here. So let's see, 200, 400, 100,000. So it should be somewhere here, but it's staying somewhere here, 0.2. It's about here. Well, at this point, I'm gonna call it quit since it's not converging right, probably due to the boundary around the sphere. The sphere is treated as smooth. Maybe here is where the boundary need to detach to get this right. So see you next time, and I hope I can have better answer for this. Have a great day. Bye.